Okay, guys, welcome. So today we're going to talk about non-homogeneous ODEs. We'll talk about what's called the method of undetermined coefficients, and we'll talk about how we can sort of in general solve a non-homogeneous second order linear ODE. So what we mean when we say non-homogeneous is now this R function on the other side of our equation is no longer just zero, right? So this is just some function of x that's non-zero. So the first thing that we need to discuss is what a general solution is going to look like, right? So a general solution of this equation is going to be the sum of what a solution, which we're going to call y sub h, a solution of the homogeneous version of your non-homogeneous ODE, and also a particular solution which we're going to call y sub p. Right, so this sort of restates what I just said sort of in a nice, concise fashion. And it says that if you have a non-homogeneous ODE, basically your solution is built up of a homogeneous version or homogeneous solution and a particular solution. Right, so essentially so the homogeneous solution we know how to do. But the question then becomes, how do we find the particular solution? And essentially what we do is we pick specific values for C1 and C2 in the homogeneous version that will satisfy the non-homogeneous version. Right. Another thing that we will discuss here is that if you have the sum of a solution to the non-homogeneous and the homogeneous solution, what you get is another solution to the non-homogeneous. And the second part of this theorem states that if you're looking at the difference of two solutions of the, again, this is non-homogeneous. If you're looking at the difference of two of those, then what their result will be a solution of the homogeneous version. So these proofs are not too terribly difficult, so I included them. So again, we're calling y in this case, we're going to be y is a solution to the non-homogeneous, so y double prime plus py prime plus qy is equal to r, and y tilde is a solution to the homogeneous version, so y double prime plus py prime plus qy is equal to 0. So as soon as you plug that into your left-hand side, what's going to happen is you're going to get a y double prime plus p times y prime plus q times y, right? And of course, that left part is a solution to the non-homogeneous version, and the part on the right-hand side is a solution to the the homogeneous part. So then, of course, if you add those two, you're going to get R, which is the right-hand side of the non-homogeneous. Okay. And then for the second part of this, if you look at two solutions to the non-homogeneous version, right? So in this case, both of these satisfy the non-homogeneous version. Then you're going to take basically the same argument, except now both of these come out to be R of X, and they'll both come out to be 0. Okay. So this next theorem basically states that a general solution of a non-homogeneous ODE, again, will include all solutions, similar to what this looked like in the homogeneous video. Right, so essentially what you need is the variable coefficients P of X and Q of X to be continuous. And of course, now we need to add in R of X. But if you have those three are continuous, then basically every solution of the non-homogeneous ODE will be a general solution of the form that we already stated. Now the proof uses some things that we haven't talked about yet, so I'm going to hold off on that for now. But if you'd like the proof, the proof for this is of course in the notes on my website. Okay, so now I want to get to how we can actually solve one of these using what's called the method of undetermined coefficients. So essentially, we're going to be looking at a non-homogeneous ODE with constant coefficients. And again, this is different to what we did before because now R of X is non-zero, right? Whereas before we looked at when R of X was 0. Okay, so the idea behind this is essentially we know that a solution is going to be the solution for the homogeneous version, which we talked about in a previous video, and we then need a particular solution of the non-homogeneous version. Now, this method is going to work if R of X is like an e to something, so we'll say e to the lambda x, or if it's like a polynomial, so we'll say a sum of a k x to the k, or if you have like cosine and sine terms, or like a combination of these, right? And the reason behind this is because the derivatives are similar to the original function. So that's going to be one thing that's sort of convenient for using this method. Okay, so what we're going to do is based on what your R of X is, you're going to have a choice to make on what our particular solution will look like. So if you have an E term, basically what you're going to do is you're going to look at a constant times E to the, basically a constant times your E term. Now, if you have a polynomial term or like a power term, basically you want the sum of that power term plus all of its preceding power terms. And then if you have either sines and cosines, you take a sum of sines and cosines, or if you have a sum of exponentials times sines and cosines, you take an exponential times the sum of sines and cosines. Now, there's three sort of additional rules in addition to how we sort of choose our particular solution. Now, the basic rule just means that you look at what your R of X is. If it's one of these functions in this column, you pick the Y sub P, and then you solve for the undetermined coefficients by plugging in the particular solution and its derivatives in. Right? Now, the modification rule basically happens when if our choice for this Y of P is already a solution. So if that's already a solution, what you then have to do is you either multiply this, your Y sub P by either X, or if it's a double root, you multiply by X squared. And then you sort of proceed as you would before. Now, the sum rule basically says that if your R of X is a sum of functions in this first column, then for YP, you just choose the sum of these different possible choices, right? So again, I think this is much easier to see with some examples, so let's go ahead and we'll do it. Okay, so for the first one that we'll look at, we'll say, what if we want to solve y double prime plus y is equal to 0.001 x squared? And of course, we get some initial conditions. So again, the first thing we do is we solve the homogeneous version of the ODE, right? So of course, what's the homogeneous version? It's replace your right-hand side with 0. And we've shown many times that this has this general solution, right? Of course, if you want to look at the characteristic polynomial, you're going to get this. And of course, that gives you plus or minus I, right? So that's where you're getting sort of the general solution there for the homogeneous version. Now, I want to sort of do something wrong here because I think I included this. Yeah, I had this previously in there, but I didn't mention it. Now, one thing that's nice about this method is that if you accidentally choose the wrong solution form, you will arrive at a contradiction somehow, right? So it sort of has a way of sort of self-checking itself. So I want to naively choose the wrong guess for YP, right? So my R of X is 0.001 x squared. So what I would need to do is, if I consult our table here, is I would need to do something like this. I would need to pick all preceding powers as well, right? But naively, I'm just going to say, let's try y sub p is kx squared. Now, if I take two derivatives, I'm going to get yp double prime is just equal to 2k, right? So if I plug this in to my ODE, I'm going to get that 2k, because this is y double prime, plus y is equal to my 0.001 x squared, right? But this tells me that if by equating coefficients that k has to equal both 0.001 and also that k has to equal 0. So that's a contradiction. So that is sort of one thing that's nice about this, is that if you choose wrong, the method will sort of work itself out and tell you that it's wrong. Now, if we correctly choose that my particular solution is not only just a constant times x squared, but also a constant times each of the preceding powers of x, then of course my second derivative will still be 2 times the constant, but it's now k2 this time. So then we get right away that k2, by equating our x squared coefficients, has to be 0.001. There's no x term on the right-hand side, so k1 has to be 0. And for the constant terms, I have that 2 times k2 plus k0 would have to be 0 since there's no constant. But we know that k2 is 0.001, and we can arrive very quickly that our k0 is minus 0.002. So then that tells us that our particular solution is 0.001 x squared minus 0.002. So now if we plug in, remember our general solution is the homogeneous solution, which is this. This is YH, plus the particular solution that we just found. That was this. This is Y sub P. So that's our general solution. Now, of course, to determine A and B, we would need to use the initial conditions. So if we use the fact that Y of 0 is 0, we get pretty quickly that A is 0.002. And if we use the fact that Y prime of 0 is 1.5, we can get that B is 1.5, and therefore our particular solution is given here. Okay, so a little bit of extra work, of course, if it's not homogeneous, but hopefully the idea is not too complicated. Okay, so let's look at another one. So now I want to solve y double prime plus 3y prime plus 2.25 times y is equal to negative 10 times e to the negative 1.5x. And we have some initial conditions that we'll consider, of course, at the end. So again, our first step is to solve the homogeneous version. So if we assume, again, that we're solving this when it's equal to 0, we would look for the characteristic equation, which will be this. And we get a double root of negative 1.5, which allows us to arrive at that general solution for the homogeneous version. Okay, now in the second step, normally what would happen, let me just indicate this is a double root here, so that's important. Now the second step, usually what we do is we would look at our right-hand side function, we go to our table, and we pick what we would need, right? So most of the time, this would suggest that I would need to, if we look at our table, let me just show you, right? We have an E term, so that would normally suggest take a constant times your E term, right? But the problem is that that's already one of the solutions, right? C times e to the negative 1.5 x is already a solution. Right? And of course, this is the idea behind the modification rule, and this says to multiply this by x or x squared, right? Now, of course, if you multiply by x, that's also a solution, right? Because this was a double root. So what you would need to do is you need to multiply by x squared. So that means that our choice for our particular solution is going to be a constant times x squared times our e term. So then we find the appropriate derivatives. So y prime will, of course, be 2x minus 1.5x squared times e to the negative 1.5x. This is all derived, of course, using the product and chain rules. And your second derivative is going to end up being this. So now if we plug this in to our ODE, this is what we're going to end up with basically once we divide through by our E term, right? So then by combining like terms and equating some coefficients, if we equate the x squared coefficients, we basically get 0 is equal to 0, so that's not helpful. And the same thing happens for x. But if we look at our constant terms, we end up with a 2c is equal to negative 10. So that allows us to conclude that c is equal to negative 5. So our particular solution is go back and replace c with negative 5. Okay, so then your general solution again is the sum of your homogeneous version and your particular solution. Right? So now again, we can use our initial conditions to find what the arbitrary constants would have to be. So y of 0 equals 1 allows us to conclude pretty quickly that c1 is equal to 1 because both of the other terms will drop out. And our second initial condition, y prime of 0 equals 0, will allow us to conclude that c2 is equal to 1.5. So again, once we plug in, we can get that our particular solution is represented by either one of these equivalent forms. Okay, so again, hopefully that's not bad. Okay, I believe this is the last example, right? Yeah, okay. So one last example, which of course will showcase the sum rule, because now this is a whole sum of terms. So we're given y double prime plus 2y prime plus 0.75y is equal to 2 times cosine of x minus 0.25 sine of x plus 0.09x, and some initial conditions. Okay, so now the homogeneous version, we can find that we can factor it in this form. So that gives us that we have two real roots. We have what lambda 1 is equal to negative 1/2 and lambda 2 is equal to negative 3/2, which gives us this general solution. Right, so now here we have the sum rule because we have sines and cosine terms. So I'm basically saying here that y p1 corresponds, it's not equal to, but it corresponds to 2 cosine x minus 0.25 sine of x. So that indicates that yp1 is k cosine of x plus m sine of x, which is here, and that the yp sub 2 corresponds to the 0.09x, which indicates that y sub p2 is constant times x plus constant. So now deriving each one of these sets of derivatives and plugging in, we're going to essentially conclude that in the sine and cosine ODE, we're going to get that k has to be 0 and m has to be 1. And in the other equation, we're going to get that k1 has to be 0.12 and k0 has to be negative 0.32. So then that gives us the general solution given here. Right? So again, this first part came from y sub h, and this second part is y sub p. Okay, so then using our initial conditions, we can get that, again, just for the sake of time, that C1 is equal to 3.1 and C2 is equal to 0. So that's something that you can and should verify on your own. That's not hard to do. So you can get that the particular solution is given by this here. Okay, now one interesting thing to note here is that if your homogeneous solution has all negative roots or all negative real parts, if you have complex eigenvalues, then one thing that's going to happen is that this homogeneous solution will approach 0 as x tends towards infinity. So what that means is that your total solution, the sum of these two solutions, is going to just simply approach your particular solution. Now, that sum of solutions is what's known as the transient state solution, or essentially while it's still moving. And, well, I shouldn't say still moving, but it's still not periodic, I guess. And once it approaches the particular solution, you have what's called a steady state solution. It was sort of settled into its long-term behavior. And this would indicate that you have a stable system. And of course, if this doesn't happen, if you don't have all negative roots, then you have an unstable system. All right, so I hope you enjoyed this video on non-homogeneous ODEs. I will see you next time.